clap until you know I deserve it at the end.
I've been here before.
Thank you. So my name is Mike. I'm usually here pretty much every month, so if you've been here before, you probably recognize me. I'm going to talk this month about EventMachine. And so, who am I? I'm a developer at OneSpot here in town, startup. And I also maintain a couple Ruby gems in Cache Client Data Fabric, and do a lot of hacking on the side. So when I say scalable processing, what am I talking about? In the last 5-10 years, Google has really made popular this notion of MapReduce, which is one mechanism by which you can sort of spread a workload across many, many machines. More traditionally, you would break up a workload into smaller units of work that you would then push onto a message queue, and then have workers, as many workers as you want, grab those messages off the message queue and process them. However, I'm not talking today about how to scale across multiple machines. Instead, I'm really here to talk about, more specifically, efficient processing. That is, how do we get the most bang for our buck when you're talking about one machine? If you've got a large node in EC2, that's costing you 40 cents per hour. If that machine's only 10% utilized, effectively it's costing you 36 cents an hour for that machine that you're not getting the value out of. So we want to focus on maximizing that machine's utilization. In data centers, the big guys, Amazon, Facebook, Google, they try to get up to 80% machine utilization. Any more than that, and you don't have headroom to deal with traffic spikes in processing. So you want to shoot for about 80% utilization of your machine to really get your bang for your buck. So what's the status quo in processing today? Well, at OneSpot, our status quo, I would imagine, is a lot like everyone else's status quo, which is we've got Ruby processes, which are single-threaded. They're several hundred megabytes in size each. And so effectively we get, let's say, 1 message per second out of these. Okay. Unfortunately, that means our load average on our machine looks something like this, which is pretty pathetic. Now what you can do is you can spin up 10 Ruby processes and maybe get 10 messages processed per second out of that machine. But you're going to be using 2 to 3 gigabytes of RAM just to do that. Not very efficient. The reason for that is that usually when you're processing a message, it's going to look something like this. You're on your CPU, then you make it called a simple DB, and you wait. And then you get the results back, you do a little more processing, then you got to go to S3. And so on and so on. You hit the database, you hit a couple of web services, all that adds up, and all of a sudden your CPU is only being utilized some small percentage of the time. So my rule of thumb is your message queue processor is going to spend 90% of the time waiting on I/O, and only 10% actually on the CPU instead. So how can we get around this? How can we get that CPU pegged 100% of the time? Well, how do we get around this blocking issue? We add indexes to the database table. We put data in memcached so that we're not blocking as long, so that we're spending more time on the CPU. But really, these are kind of workarounds to the underlying issue, which is we have to block and sit there waiting for the data that we need to process. And like it or not, blocking I/O is everywhere. Anytime you do file, SQL queries for the database, even hitting memcache is a blocking I/O call. It's a really fast blocking I/O call, but it's still blocking. Calling out to web services, even something that you don't even think of, like a DNS lookup. To hit a web service, first thing you need to do is call out to your DNS server to get its IP address first. That's blocking. Even something like shelling out to a child process is blocking. You got to wait for that child process to return. So, again, the question is, how do we maximize this blue? I want a straight blue bar across time so that I know the machine's being pegged and being utilized efficiently. So the answer in other systems is threading. In the Java VM, you'd spin up 10 threads, have each thread take an operation, and you process 10 messages concurrently. If each process, or I'm sorry, if each operation is taking 10% of the CPU, and you're doing 10 concurrently, theoretically you should be able to get 100% CPU utilization. So that's great for Java, but unfortunately it's not good for Ruby. The reason is that Ruby has this legacy of thread unsafety and just being generally hostile to threads. Extensions and Ruby libraries are thread unsafe. Until Rails 2.2, well, I should say Rails was not thread safe until Rails 2.2. On top of this, Ruby's had poor thread implementation. Ruby 1.8 has green threads. Green threads means the operating system doesn't know anything about the threads. And as a result, your threads don't use more than one CPU at a time. You have to use native threads to have threads executing on multiple CPUs at the same time. Ruby 1.9 has native threads. But unfortunately, because of this history of thread unsafe extensions and libraries, Ruby 1.9 does not allow Ruby code to execute on more than one thread concurrently. It has what's called a global interpreter lock. And so if Ruby is executing in one thread on a core, all the other Ruby threads are locked out and cannot execute at the same time. JRuby is the only good threaded solution. If you do need multi-threading, you can use JRuby. MacRuby also has a good threading solution. Of course, it's less mature than JRuby. So what we need is something that will allow Ruby to have one operation on the CPU while other operations are waiting on blocking I/O. That would allow us to fill in the green gaps so that we can get solid blue all the way on that timeline. But we can't use threads because Ruby doesn't do threading. And that's essentially what asynchronous or evented I/O is. We have two operations here. The second one's on the CPU. It makes a blocking I/O call, and we flip to the other operation. Right? Once that first operation makes a blocking I/O call, and then we wait for one of those I/Os to finish. The second operation's I/O finishes, it starts up on the CPU again. And we have this ping pong effect where we're ping ponging between all these various different operations based on who can run at a given moment in time. So that is essentially what EventMachine gives you. EventMachine is a Ruby implementation of what's called the reactor pattern. I've got a definition here of it. The reactor pattern is a concurrent programming pattern for handling service requests delivered concurrently to a service handler by one or more inputs. The service handler then demultiplexes the incoming requests and dispatches them synchronously to the associated request handlers. That probably doesn't mean anything at all to any of you. It certainly doesn't make a lot of sense to me. But that's essentially a long-winded way of saying what I just said, which is it's a pattern which allows us to interleave multiple operations based on their I/O. Only one of those operations will be on the CPU at any given moment in time. And like I said, it's single-threaded, so we don't have to worry about thread safety in our code. So how does it work? Well, in a word, the select system call. The select system call has been in Unix for decades now. If you want to know the low-level details of exactly how EventMachine works, I suggest you read up on the system call and get a feel for what it does. Essentially, what it does is the application passes in a set of I/O operations or file descriptors that it's interested in knowing when these I/O operations are available for reading, writing, or errors. And the operating system then takes care of waiting on that stuff. The operating system does it, a lot more efficiently than an application can. Now, in the few decades since Select became available, there's higher performance versions of the Select call. There's epoll on Linux, KQ, and devpoll on Solaris. So anytime you see sort of an event-driven system, oftentimes you'll see we support these four mechanisms for doing event-driven I/O. I don't know the first thing about Windows anymore, and I'm sure something like Select is available on Windows, but I don't know the specifics of it. I do believe that EventMachine does support Windows, but you'll have to do your own investigation if Windows is a concern to you. So this all sounds perfect, right? Well, it's not without issues. There are some limitations, some interesting side effects to this. The first side effect to the reactor pattern is inversion of control. Your code no longer executes as step A, step B, step C. And that's because it happens asynchronously. What instead you do is you say, I want to call A, and then you pass in a callback that EventMachine will execute once A is finished. So instead of A, B, C, you get a series of nested operations, nested blocks where you say, do A, and then when that is done, do B. And so you get a, instead of a clean step 1, 2, 3 flow, you get a series of nested blocks. Error handling is difficult because exceptions aren't thrown through your code, they're thrown into EventMachine. Okay, so it can be a lot harder to figure out if something goes wrong and to recover from that error. Fibers do make the application code a little bit cleaner. I'll explain how that works here shortly. So this is this is what it looks like. This is what I was talking about. I'm going to spend a little bit of time on this slide because it's important. This is one of the key slides to understand, but this is essentially what EventMachine code looks like. First thing we're doing is we're calling em_run. That starts the reactor. You have to have a reactor running to use EventMachine, period. Within the reactor, we have a block that executes. That's our application code. Okay. Now in this case, our application code is just three statements. First thing we do is we're going to make a SQL query, then we're going to write to S3, then we're going to write to simple DB. When all that's done, we're going to stop the reactor, which effectively exits our application. However, that's not the order in which things execute. First, one executes. That calls make SQL query. Make SQL query sets up the asynchronous call with EventMachine, and then returns. The code within that do block does not execute right now. It executes at some point in the future when that SQL query has returned with the data. As Ruby developers, we're used to passing in a block to a method. And usually that method executes that block internally, right? So the block sort of executes during that method invocation. That's not the case for EventMachine code. This is a true callback. It's being called some point in the future. So one executes, and then two executes. Okay? Now our application code is done. It's finished. The only thing we've done is we've told EventMachine, send the SQL to the database and then wait for the response. Once the response comes back, then your block is called with the results. Then 3 is executed. The exact same thing happens again. We set up our call to S3 and then we exit. Our callback will be called some point in the future. Once S3 is responded, then it calls the callback, which executes 4. Same thing happens, and then once SDB has responded, then we can stop the reactor and we're done. That's essentially the way EventMachine code looks on Ruby 1.8, a series of nested callbacks. Now fibers make things a lot easier, a lot simpler to sort of understand. Because a fiber, you can do your own control over the way code executes. You don't need to use callbacks. You can make it look like you're not using callbacks. Essentially what we're doing here is we make it look like we're doing A, B, C. And the way we do that is we hide inside each of these methods some fiber magic, which makes our asynchronous code look like it's blocking or synchronous. The way that works is we grab the current fiber, we set up our asynchronous call with EventMachine, passing in a block, and all that block is going to do is resume our fiber once that call is finished. And then fiber yield is called. And fiber yield just says, stop my application code from running and give control back to some other fiber. That some other fiber is going to be what EventMachine is running on. Yeah? fiber is 1.9 only. What's that?
Could you describe it?
Sure. A fiber is a green thread, essentially a user-level thread. It's it's like a thread, except the Ruby doesn't know anything about it. The operating system doesn't know anything about it, or rather, it doesn't control it. You have to explicitly give up control. You have to yield for the system to context switch to another fiber. So it's like a normal thread, except you control the context switching. So what we're doing here is we're giving up execution to EventMachine. EventMachine has already had this asynchronous call set up, so it's listening, waiting for that I/O to come back. Once it comes back, it calls this callback, and all that callback does is resume the fiber's execution. We pass in the arguments to it, and those arguments are what's returned from fiber yield. So essentially, we're doing a callback, but to our code in the EM run block, it looks like a blocking call. And so that way, EventMachine code can look a lot more like normal Ruby code. That's easier to understand. Any questions so far?
Yeah.
Yeah.
So I can't quite resolve the blue stuff to the left of the SQL query, but where does the things that do stuff go? Does any of it go down there in the, so there's the part that has the fiber def method params,
Mm-hmm.
and then there's the part up at the top. Where is it that you do stuff?
Async call. So make SQL query, you might pass in some parameters to make SQL query, like say the string of SQL that you want to execute, right? That would be passed into async call to be sent to the database.
And so then the stuff where I actually call the database goes right above fiber.resume?
No, the actual calling of the EventMachine APIs to set up sort of the actual call would go in async call.
So my application logic, like the part where I would turn a hash of conditions and actually construct a query. And
you would probably want to do that outside of this method.
Okay.
But you could easily these args that are passed back. This is what the database is returning to you. So you would turn this args into a result set that you could then turn into a hash. I've got an example of a database adapter, a database driver, later on in the presentation, and that might show you a more real-world example of what's going on.
Can you say what that blue stuff says? I can't read it.
Which blue stuff?
The dark blue.
The dark blue in the second, third, fourth lines.
Right here?
Dot, 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 some dark blue.
Well, that would just
Make
be,
SQL.
this would just be the results.
What are those characters?
What is the blue? What is the character?
It looks just like a blue blob to me.
Right here, an equal sign.
Oh, yeah,
Okay.
I can't tell.
Can't see that. So my question, great, my question is that dot, 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 the block that's over here on the left picture?
That
So
would be,
all
that
your
would be
code
the
in the
results.
Huh?
This would be the results of this method invocation, which would be the same thing as the results here.
So all that code in your block
Mm-hmm.
would be over there in a block that says equals make SQL query.
I guess what I'm trying to say here is that we call make SQL query here, and EventMachine will pass us in some results as arguments to the block, to the callback, right? It's the sort of the same things happening here. We're calling the method, and then we're returning from the method what EventMachine returns to us.
But I guess the question is, if you, after you make the SQL query, you want to run 30 lines of code, where is that 30 lines of code?
It can be between these two method calls. Yeah.
Is this essentially like the old Windows cooperative multitasking?
Fibers are definitely cooperative multitasking, yes.
Okay, thank you.
Good question.
So your calls here is synchronous though in this example, right? I mean,
Yes. Well, it's synchronous in that this fiber is yielding, and then it's not going to start executing until this async call, until EventMachine calls this callback.
Right, but like make SQL query and write it. All those are synchronous calls. They're not going to execute until the previous.
Correct. Correct. That's what I'm trying to say about fibers. Is fibers make it look like it's procedural now. You're executing 1, then 2, then 3. Even though under the covers it's actually it's asynchronous. And by doing this asynchronously, we can allow other fibers execute in tandem. So now we can get that 10 operations executing concurrently by having these fibers they're all yielding, we're ping-ponging between the different fibers as they perform I/O. Okay, good so far? Any other questions? Okay. So, as you can see from the previous slide, the code is hard to understand, especially without fibers. You get this series of nested blocks. It's hard to understand the code flow. On top of that, the EventMachine website's not that great. The examples they have are how to set up like a TCP server that echoes hello world. It's just not a good real world example of solving a problem in the real world. There's also this learning curve of just understanding all this. This stuff takes a month or two to sort of grok. And, I've slowly had to work with it on weekends to get a feel of how things work. On top of that, testing is very difficult. With tests, you're used to saying just call this method and then check the return values. But with EventMachine code, you can't do that. You have to set up this global reactor first. And then not only that, but you have to execute that code within the reactor, and then the test has to wait until things are done. But because things are executed asynchronously, it's hard to deal with that. So in the test unit, you have to set up and tear down a reactor, which is hard to do because test unit doesn't have a way of injecting a block that surrounds a test. So you have to write a lot of testing infrastructure to test EventMachine code, unfortunately. One of the bigger issues is what I call whack-a-mole, which is your Ruby processes do a lot of blocking I/O. I've enumerated them all, or not all of them, but I've enumerated a lot of them. You access the network, you do DNS resolution, you hit the database, you access the web service. All this stuff is blocking I/O, and the more you move your blocking I/O to EventMachine, the more you gain places where you can get concurrency. But the converse is true. The more blocking I/O you do, the less concurrency you get. And so, let's say your database driver is not asynchronous. Anytime you hit the database and wait for a query to come back, your process is sitting there dead. Nothing's happening because EventMachine doesn't know that it can run other operations in the meantime. So you have to translate a lot of your I/O to EventMachine before you'll start to see the scalability promises in it. So let's look at some code examples that you can sort of get a better feel for some real-world EventMachine code. As I said before, the EventMachine website's not very good with samples and examples, so I set up my own GitHub repository and started writing some event-driven gems and libraries and whatnot that actually solve real problems that you can go and you can check out, read through, sort of see how I'm solving various issues. The first one is what I call thumbnailer. This is some rack middleware that runs on Thin that dynamically creates thumbnails from images that are stored in S3. This is actually in production at one spot. It's on Ruby 1.8. It does not use fibers. Here's sort of what the core code looks like. It's rack middleware, so you just have a call method which is passed in a request object. We just translate that request object, or we translate that environment into sort of this, what I call the image request object. And then all we do is we tell EventMachine at some point, at the next available moment, please execute this block, and then we return asynchronous response. That's it. That's all the rack middleware does when it initially executes. Once the asynchronous response has been returned, then Thin can go and handle other connections. But at some point in the future, we're going to call this next tick callback. And this next tick callback sets up an HTTP request to S3 with the location of the image and says, get me this get me this file. That's all it does. It sets up a callback to be called when it's done, but then it's finished. And then at some point in the future, once that S3 is done, then the callback is called. We take the response body, we convert it to a thumbnail, and then we tell Thin, hey, I'm done with this response. Here's the bytes of the thumbnail. It's at 200. We're done. Obviously, I've removed a lot of error handling and stuff like that. The actual real world code is in my evented repository. I've snipped a lot of it out so that I can fit this code on one page. But at the heart of it, it's not very complex.
So the browser then is sitting and waiting?
Yes.
Is that right?
There's an open socket to the browser.
Okay.
It's just nobody's doing anything with it until we call body.succeed. Then everything's written out. It's a little magical trying to understand how the APIs work. That's why I like to see real world examples so that you can see how people have solved problems. And this code took me a day or two to figure out how to write it. Hopefully it'll save you a couple hours if you decide to use EventMachine.
So what we're looking at here, all the different classes and things that we can see, what parts of this are actually EventMachine API? Like deferrable body.
EventMachine next tick.
Okay, what's deferrable body?
Deferrable body is something that comes with Thin, I believe.
Asynchronous response, is that
Async callback is a Thin thing. Rack does not support asynchronous responses right now, so Thin had to sort of create its own standard of how to do that.
Thin is
And
built
so,
on,
I'm sorry?
Thin is built on EventMachine, right?
Yes, Thin is a web server, EventMachine based web server. So Thin had to come up with this standards by which you could tell it to use asynchronous response. There's an asynchronous response object up at the top. And if you know Rack, you return three things. You return first the status code of the response, you return a hash of headers, and then you return an array which represents the body, the response body. And for Thin, to tell it to use an asynchronous response, you return -1. And then in the environment object that you're passed in, there will be an async.callback thing that you can call, which says, okay, I'm done with the response. Now you can stream it out to the socket and give the browser the data that it's requesting. Any questions? Yes.
So is that the only Ruby web server that you can use the machine with this way, or do you know of any others?
I only know of Thin. That is a robust web server, EventMachine-based web server. Certainly, EventMachine is a library by which you can create event-driven servers in general. So you could write your own HTTP server if you wanted to, but I wouldn't recommend it.
Okay, right on.
Yeah. Thin is essentially, it's EventMachine plus Mongrel's HTTP parser, which is really super fast. So it's kind of, best of breed, taking a bunch of components and throwing them together. So it's actually got some pretty nice performance.
My other question is this EventMachine HTTP request. Is that a whole separate library, or is it related to any other HTTP libraries that we know?
That is a separate library. It's called em-http-request. It was written by Ilya Grigorik of PostRank, yeah. But PostRank is a big event-driven EventMachine company. A lot of their infrastructure runs on EventMachine. So he's a big resource when it comes to EventMachine type information.
This may be a stupid question, but so you did this so all the requests, the people requesting to whatever they're doing, generate images or whatever, don't get queued up behind one another as the thumbnails are getting created?
That's actually a good question. It's a really good question. Yes, exactly. If you think about deploying a Rails app, we used to use Mongrel. Some of you probably still do use Mongrel, but remember you'd fire up 5 or 6 or 7 mongrels. Well, why would you fire up all those? Because mongrel can only handle 1 request at a time, at least before Rails was thread safe. So if you wanted to handle multiple requests at the same time, you had to have multiple mongrels. Well, within an event machine, you're not using threads, but each one of these requests is an operation. So while this operation is waiting for S3 to come back, you can have other requests coming in and queuing up and firing off their own S3 requests. So yes, exactly. It's a way of getting concurrency so that this single process can handle multiple requests at the same time.
Are keep alive sent managed and stuff like that? Keep the waiting connection alive? Doesn't the browsers kind of say where's my data and forget about it after a certain amount of time?
Well, after I think browsers are default to about 2 minutes for a timeout. Yeah. And you don't
there
need
is such a thing as a TCP keep alive.
Yeah.
That's happened at the TCP stack layer, which the operating system is doing regardless.
Okay.
So that's not an issue.
Right. Another thing to note is if you remember that whack-a-mole slide where I said blocking I/O is everywhere, you got to be careful, otherwise you'll lose your concurrency. There's 2 places where I'm doing blocking I/O here. Anybody know where?
File read.
File read, exactly. There's no, that I know of, there's no asynchronous file I/O. EventMachine does not have an API to do it. And as far as I know, Ruby obviously wouldn't tie into EventMachine, so that file read is blocking. But because I'm reading a little 8K thumbnail off of the hard drive, I figured it's probably not that big of a deal. The other one is the DNS lookup of S3. I'm resolving that host. That's a blocking call. I actually have no idea how to do an asynchronous DNS resolution in EventMachine. So if anybody knows, let me know.
What about two-thumb actually processing?
Two-thumb is it's an image science which is in memory, but it's actually writing it to the file system, the generated thumbnail to the file system. So yeah, in the two-thumb method there is a little more blocking I/O. Yeah, if I wanted to go for absolute scalability and concurrency, obviously I'd want to make some effort to asynchronize those operations too. But for right now, it hasn't been an issue.
So, say you're applying this in an app, say 100 screens or more. Do you keep this EventMachine.nextTick do close to every I/O operation, or do you abstract up to a higher level and have it wrap, say, common things?
In general, I would say you want to hide as much of this sort of infrastructure, API infrastructure, away from the application code as possible. Right? You want this stuff buried down in the guts of your infrastructure. You don't want to have your app developers know and care.
That's why you want one line that calls .nextTick in the whole app?
No, that's not what I'm saying necessarily. I'm saying that ideally this would be hid from the application developers. They would not know that they need to call this. They would just call some other API. Right? That's why I like fibers, because they allow you to wrap these asynchronous calls so that they look synchronous. You can build what looks to be a synchronous API on top of an EventMachine. Nobody's the wiser. The next example is what I call Quinaut. It's an SQS processing daemon that I wrote, much because of this presentation. It's the next generation message processor at one spot. Our current processor, like I said, is 1 message a second, single-threaded, taking hundreds of megabytes per process. And the idea with Quinaut is that it's going to handle 5 or 10 messages concurrently for the same amount of RAM, or approximately the same amount of RAM, and thereby get us much better machine utilization. And it's got event-based Amazon Web Service APIs for all the major APIs. And it uses fibers with Ruby 1.9 so that the code, the message processing code that you use, looks like normal Ruby code. To his point, you want your application developers not to know or care that you're using event-based APIs. To them, it just looks like they're making a SQL query, and then based on the results, they're writing a file here. They don't care. Has anyone here used the EventMagick library? The EventMagick library allows you to say, give me the information about a particular image file. So you get the type of the image, whether it's a JPEG or a PNG or a GIF. You can get the size of it. All this is important when you're doing image processing. Well, we use EventMagick. And just like any of the other blocking I/O sources I told you about, EventMagick shells out the ImageMagick binary on the command line to actually do its work. So that's a system call, and so that's blocking I/O. So I wrote an evented version of EventMagick called EventMagick, which just ports it to use the EM system call, which is asynchronous. And I did some benchmarking, and it turns out it roughly doubles the throughput. If you fire off a bunch of operations to identify a bunch of JPEGs, it roughly doubles the throughput. This is how it's implemented. The run command method up here is essentially what EventMagick is executing. The key thing is this execute method here. In EventMagick, it's this implementation down here, which is blocking. It's just using the backticks to execute a command, and then returning the output of the command along with the status, the exit code of the process. I wrote an event-driven version of that method called evented execute, which just uses fibers to make it look like the exact same. It returns the exact same data, so EventMagick doesn't know the difference. And so we can switch between blocking execute and evented execute really, really simply. And again, for those 5 or 10 lines of code change, you get roughly double the throughput. We use PostgreSQL at one spot, and so any sort of evented code that we were to write would scalability would suffer a lot if we didn't have a database driver. Unfortunately, no one stepped up and wrote a driver for PostgreSQL for Active Record in EventMachine, so I stepped up and did it. It requires Ruby 1.9 because Active Record is a blocking API. That is, it calls the database driver and then it expects it to return the results. So it uses fibers so that it looks like a blocking API. It's on my GitHub. Y'all can check it out if you use PostgreSQL. There is an asynchronous database driver for MySQL called MySQL Plus. If you use MySQL, you just use that. It's pretty simple. But the key to implementing this database driver was actually pretty simple, because a database driver at the heart of it, it's just a single method, which basically says send this SQL to the database and then get the results back. That's 99% of the guts of most database drivers. So really all I had to event was one method, this execute method. And you can see we're doing the same fiber stuff that I showed earlier in my slides. Grabbing the current fiber, we're setting up the asynchronous call, so we passed in the SQL. We're calling the query method to actually set up the database connection and fire off the SQL. And then we're telling it, here's the success callback, or here's the callback that you call it either way. And that passes us in a couple parameters. When we yield, we know that when the yield returns, that we're going to get those 3 parameters that were passed into the block. And then if status is true, then that means the call succeeded. We just translate that into a Postgres result object and return it. And that's all Active Record expects. Active Record just expects this PG result object.
So the query with a callback, is that part of the underlying driver?
That's part of the underlying EventMachine Postgres 3 protocol. It provides this asynchronous API. And I just wrote this execute method as a synchronous version of that API using fibers. Yes.
Where's the callback method coming from? Is that coming from EventMachine?
Yes, that's
Okay.
that's in
Not
this
Fiber.
that's in this Postgres 3 protocol that EventMachine implements. So EventMachine does provide this asynchronous API, but again, it requires callbacks for everything. So I just made this execute method, which takes that asynchronous API and makes it look synchronous so that it works with active record. Any other questions? Yes.
Can you step through that and say when each of those lines happens?
Sure, sure. So first we get the current fiber. We set up the query. All right, and that hands us back a what's called a deferrable. And the deferrable is something that EventMachine will call back once it is finished.
All right, so query, that's not part of active record, that's part of
It's part of EventMachine.
EventMachine.
Yes. This query method
Uh-huh.
is in this class, Postgres 3 class.
Okay.
We're adding another method to this class that is a synchronous version.
EventMachine provides that class Postgres 3?
Yes.
Why?
It provides a number of protocols that are asynchronous versions. It provides a memcached protocol.
So they just kind of picked them out of like the commonly used?
Yes, exactly.
Okay.
There's a HTTP client, for instance. Okay, so query returns a deferrable object. One of the methods on deferrable is callback, which says, when this deferrable is finished, call this block. So essentially, we're just calling this method to tell EventMachine, call this block when this query is finished. Okay? So this executes, and then we jump down to fiber yield. Fiber yield executes, and then we're done. We pause. This fiber stops. Data EventMachine, the execution goes back into EventMachine. It fires off the SQL onto the socket, and then calls IO select, the select system call to wait, essentially, for that to return. Once it returns, it's associated the deferrable with the select operation. So once data comes back, it knows that this deferrable is done. It calls the set of callbacks that have already been associated with that deferrable. 99% of the time, you're only going to have one callback, the one callback that we set up. So it's going to execute this callback now. All it does is call fiber resume, and then boom, our application is executing again. We return the arguments to the callback, and now we're just doing our business as usual.
And Ruby is the thing that's handling that what seems weird, having never used fibers, where the remainder of the method actually isn't run. It's just right, like all the lines after the fiber yield. Those aren't like fiber yield.
It's an asynchronous
it's
break.
Like a weird return.
Yeah, effectively what's happening is this executes, which transfers control to some other fiber somewhere else.
Okay.
Fibers are literally user-controlled threads. So you've got multiple fibers executing, but only one at a time. And so you jump from one to another, and you could jump anywhere, but you only jump to places where you've yielded.
So that yield pauses until the resume is called.
Exactly.
Does it pause into the resume? Okay, I got you. So when you call fiber.yield, it jumps into the query SQL callback.
It jumps into some other fiber that's ready to run. 99% of the time, that's going to be the root fiber, which is what EventMachine should be running on. Okay. The only thing in that root fiber is just the EventMachine core, where it knows I'm listening for successful I/O operations. Right. Once those I/O operations are done, it just calls back into whatever callbacks have been set up.
Essentially, fiber yield is a method call that never returns.
It does return.
It does
No, it doesn't return, you get called the callback.
It returns when you
Resume
send
by
the call.
fiber resume says resume wherever you left off.
And that does the return.
Okay.
One thing to remember is that Ruby blocks are lazy evaluation, and that block is sort of executed. All that's done is the code is stored someplace.
Right.
And then it will not actually execute until when EventMachine says, I'm ready to do you. So that, that block in there does not get executed, right after the callback.
And notice we're having to use Ruby's closures because we have to keep track of which fiber was current when this callback executes. We can't call fiber.current.resume because the fiber that this callback is called on is the EventMachine fiber, right? You have to transfer control from EventMachine into my application's fiber. And so I need to store that fiber here so that in the callback I can resume it. Does that make sense? It's a real mind twist, and this is why EventMachine is difficult to understand. The code flow is not 1, 2, 3. Sometimes it's 1, 3, 2. Any other questions so far? Yeah.
So somewhere way up your stack in your controller, you've got like a find call. So that find call is blocking or not blocking. It continues because of this code.
This method is for all intents and purposes synchronous, right?
Yes, yes. This method is synchronous to the outside world. The outside world does not know that internally it's asynchronous because of the fiber yield and resume business. That's what turns the asynchronous API into a synchronous API. And that's why Active Record can use it. Because Active Record just expects to call exec with a SQL statement and then get a result set back. It does not expect to pass in a block, which is called when the SQL's ready, right?
Yeah, so your find in your controller is going to block, but if you've got multiple controller accesses simultaneously, then in theory, this is going to enable them to complete much faster.
You're not trying to make the one find faster,
Yeah.
you're trying to make all the simultaneous.
Yeah, that's what
finds faster.
Exactly. You're still going to want to set up indexes, something like that, because that'll make the asynchronous call come back sooner, right? But the asynchronicity allows us to handle more than one operation concurrently.
Well, just to make sure, in your controller, let's say, hypothetically, you have 3 finds. It's no faster than Active Record today. This example.
Correct.
No faster.
Correct.
Okay. Just making sure.
It's not a way of improving performance. It's a way of improving concurrency or scalability without using threads. Yes.
How would you do this in one without fibers?
In 1.8.
Yeah, without fiber.
You can.
Okay.
You might be able to use continuations or call CC. Call CC is a way of implementing, it's how fibers are implemented in C. I don't know how many of you know the call CC standard C function, but it's essentially what's behind this business of jumping from one part of the code to another without like unrolling the stack, essentially. It's tough to understand, but you would have to implement either, no matter what you do, you're going to have something like a fiber if you want to turn an asynchronous I/O into a synchronous I/O. Okay.
So how would you actually take advantage of this? Is where I'm confused. So you just said no faster than any normal active record. So I actually have to run. Is it just multiple process? I mean, obviously, then that's what we're back to what we always did.
No, the point is while this fiber has yielded to EventMachine, some other operation can be on the CPU processing.
But you'd have to actually set that up with other fiber yields, right? Or other fibers.
The point is that any blocking I/O that you do, if you set it up to use EventMachine, EventMachine can context switch to other operations while your operation is paused, waiting for the database results. Sorry?
So that could be anything. That could be another thread, anything.
Well, the idea is we're not using threads here.
I know that's what I'm. That's why I'm
But
confused.
the point is something like Thin would set up each request to be its own fiber. Okay, so you can have multiple requests processing concurrently. Because while one request is waiting for the database, another fiber, another request on another fiber, maybe hitting memcache, maybe hitting a web service.
So you need Fin on top of this to take advantage of it.
You have to have EventMachine running, right, in some sort of container.
If you only used it in this one spot, it wouldn't help you at all. You have to use it here, and then you have to use it in the request cycle. You have to use it all
Well,
over.
this assumes that you've set up your code to run within a fiber. You have to have a current fiber for this to work, right? So that is again, that's part of the global context that needs to be set up outside of your application code.
It says it's not running on, it's not Ruby threads, but isn't it operating system threads? And if not, aren't threads still there? It's just the operating system is managing those threads instead of being Ruby threads?
Well,
no, this is not.
Well, I explained it in a previous slide about threads, but Ruby's threads are not implemented very well in terms of scalability. So Ruby 1.8 doesn't even have operating system threads. It has user threads, which are essentially fibers. And Ruby just context switches between them. It's on its own. The operating system doesn't know anything about it, and so therefore they only run on one CPU. Okay. In Ruby 1.9, you have real, actual native threads, but because there's a global interpreter lock, you can only have Ruby executing on one thread at a time. You essentially can't take advantage of multiple cores with threads in Ruby. Anything else?
This isn't taking advantage of multiple cores either, right?
Correct. EventMachine will peg a single core, but because we're single-threaded, we're only going to run on a single processor.
So if you're on a 4-way box, you may be running multiple event machines.
I'm sorry, say that again?
Would you run multiple event machines on the same box?
You run 4 cores, 4 processes. Yes, and then each process can peg a core.
At least that's simpler than what we do today, which is kind of just guesstimate.
Yeah, well, exactly. Like I was saying, at one spot, we do one message per process at a time. So we fire up 10 of them, and each one takes up 200, 300 megs. Now you're talking 2 or 3 gigabytes of RAM. If you can do the same amount of work with only 2 or 3 processes, you dramatically drop the amount of RAM you need, while also guaranteeing that you're going to peg your CPUs.
I think you had this before, but could you sort of explain what happens when you call the yield method on the fiber class? What's really going on there? And that's too below the,
It's really hard to explain, and I'm not sure I can explain it very well, much less if I understand it very well. But I would do a little research if you're interested. Go to Wikipedia and look up user threads or green threads. Look up the call CC method in the C standard library. Yeah, I mean, essentially what you're doing is you're jumping from one place in the code to another without the normal unrolling of the stack. So you're not returning from the method to go somewhere else. You're just literally jumping from one point of execution to another. Again, I don't know how to explain it very well.
What's getting executed? I mean, the block is getting executed on fiber yield, and is that because there is a fiber that is that is lifted by that closure?
What we've done is we've said that we've told EventMachine that we want to execute this SQL, right? And then we've also told it when that SQL is finished, execute this callback, execute this block. Okay? And then we yield. That yield transfers control to EventMachine. Now all EventMachine knows is when that query is done, it jumps back into that callback.
So is EventMachine hooking into the fiber infrastructure?
No. All EventMachine knows about is this callback. Okay? It doesn't know anything about fibers. But this callback knows about fibers.
Right. So is fiber.yield executing fiber.resume?
Fiber.yield is control of EventMachine. And EventMachine is going to invoke that callback, which then calls fiber.resume. Right. So in a way, what you're trying to say, I think, is that this code these lines are executed on the application's fiber. This line is executed on EventMachine's fiber.
Okay.
The thing that might clarify this is to stop thinking about fibers like you normally think of threads where you yield and it goes to some random fiber. That's not how fibers work in Ruby or indeed in a lot of cooperative threading. What happens is there's some original fiber, which of course would be EventMachine in this case. And when you create a fiber, it's not running. You have to explicitly resume it for the fiber to run in the first place, which is what has happened at some point, through thin in your case, but right, somewhere along the line. For example, when the connection is accepted, it will start the fiber and pass it in and go. Now, when you say yield, it specifically goes back to the thread that resumed it. That means EventMachine. In other words, think of it like spokes. EventMachine is calling out to whatever fibers it wants, which runs for a period of time and says yield. And at that moment, it goes back to the center of the spoke. So it's not like, you know, when you normally think of threads, you think of like a million things going at once, and the operating system's allowing crap to run, and some complicated design of what's been stalled out and priorities and all kinds of stuff. None of that is valid for fibers. When you say yield, it goes back to the fiber that was resumed. End of story.
Yeah, I forgot about that.
It's really like a stack-based call thingy. Like that's a better way to think of it. Because when you say yield, it pops the stack back to the previous fiber. It just also preserves where you were.
Right.
So that when you say resume, it can put that arm of the stack back on.
That's a good point.
So
Thank you.
is one spot, not a technical question, is one spot seeing some, you know, was there some financial throughput problem in dealing with Amazon and your scale that necessitated this? You're preparing for more growth? Is this more manageable? Are you making more money for this?
Yes and no. Next question. I mean, you know, I just think it's ridiculous that we should have a several hundred megabyte process,
right,
which is using a tenth of the CPU and processing a message per second.
You did this on principle because it was an improvement that could be done, and it was reachable.
We're like a huge user of Amazon's APIs.
Mm-hmm.
I mean, we've got an account rep there, and they know us. I mean, we're paying them a pretty penny every month, and we want to get the maximum utilization for our dollar. So that's exactly what this translates into, and that's why I'm somewhat offended by our current system and how inefficient it is.
There's also a flexibility thing. I also worked at one spot, so we have a lot of different queues, and we have different processors for those queues. But to avoid having all these processors, we sort of glom some of those together. Where you have, you know, you can put multiple different kinds of messages on a single queue, and then that processor will pull it off. And it would be, and sometimes a message of a certain kind will fill up the queue, and the other kinds get starved for a little while. It'd be more efficient from a scalability standpoint to have, you know, dedicated types of processors and separate queues for every kind of message. But if that specific kind of process doesn't happen frequently enough, you can't really justify the cost of having all these idle processes sitting around waiting to manage queues that are mostly empty. And so here we can deal with that in a much more effective way.
How far have you pushed this from complexity of the application? Certainly, you know, the thumbnail application ends up being pretty, you know, at least non-complicated logic, pretty straightforward solution. Even the driver here ends up a pretty straightforward solution. How far have you pushed this in terms of program complexity? And I'm wondering what that translates to really from like maintenance and debug, you know, problem resolution type headache. I'm thinking we've got a big migration tool that's running 35 Ruby processes to try to move data from a legacy system to a new system, and are queuing and doing a bunch of work. And it's I know it's got tons of blocking IOs. We're reading from a legacy database, munging some data up and pushing it into new. But I'm hesitant to say. I mean, we've got thousands of lines of code in there. You know, what would introducing something like this do to it from a
That's why I've sort of stressed fibers in Ruby 1.9 here. Fibers are only in Ruby 1.9. But because of APIs like this, you can essentially make your blocking I/O into asynchronous I/O while making it look like it's blocking to your higher level application code. And so that means that you don't need to retrain developers on a totally different way of writing Ruby code. That's why I'm not a big fan of EventMachine and Ruby 1.8. Because like it or not, you have to do that callback style, which is completely different from the way we're used to looking at Ruby code. But when you harness the power of fibers here, you can basically turn any API into a normal looking procedural API.
You still end up with stuff like this too if your I/O bandwidth is pegged by what you're already doing. This isn't going to help you out either, right?
Yes.
So you have to know that you have more bandwidth in your I/O to say I want to kick off more I/O concurrently, and there's space for that.
Yeah, I mean, if your Ruby processes right now are filling up the pipe, then you're good to go. But I mean, if it's taking 10 Ruby processes and
Sure.
2 gigabytes of memory to fill up that pipe, maybe you can fill up the pipe with 1 Ruby process and 250 megs instead.
So to pathetically volunteer somebody else, Bob, do you want to? I mean, we've used EventMachine a bunch. Can you? What are the use cases? I think there's 2 real ones for us that have been useful: processing queues and then mass fetches of like a whole bunch of HTTP requests at once.
Yeah, so we have a part of our application which has to generate an RSS feed from like multiple S3 objects. So we have a Rails thing that doesn't use fibers, it actually uses threads to kind of do the same thing that you're doing there with fibers. But we use it so the user doesn't have to wait for us to do 25 sequential things there.
You can use asynchronous HTTP APIs that don't use EventMachine necessarily.
Right.
Like Typhus, lib multi-curl, I think, multi-curl will also do, you can say fetch these 20 web pages, and it'll go out and fetch all 20 at the same time, and it'll return once all 20 have come back. So you don't have to do 20 one at a time. You're doing 20 in parallel effectively. And essentially what it's doing internally is it's setting up a little mini reactor, setting up each of those calls, and then the reactor shuts down and returns the data once it's done. So it's like a little tiny event machine that's being run at that just for that one API call. Yes.
So that brings up an interesting question. Let's say you want to do what you just said. You start with a mini reactor and return something. So obviously you can't literally return from the outer reactor run because that returns immediately. So how do you return something that comes out of the inner block? Whether I guess with fibers, that's the answer, right? Like use fibers and that's not an issue.
I guess. I guess your question is so abstract that I'm not sure how to answer it.
Well, in your Ruby 1.8 EventMachine thing, you had nested blocks. How do you return something from the inner block to somewhere else? Like you just said, I have 20 things. When
You
it's
can
done.
use
Yes,
closures, right? You set a
Yeah.
variable to nil on the outside of it,
Yeah.
and then in the callback you set its value to something. And once that block is done, the value of the outer variable should be set. Okay, anything else?
Let's see more of your slides.
Yeah, I was going to say, this is a long slide. And the stock's gone on long. Glad the other guy didn't make it, I guess.
Mike, I guess I have one question. Say you've got enough memory. That you can have multiple Rubies running. Would this have an advantage over, say, running like Passenger, where it's just running multiple instances of Ruby?
Does anyone have any opinions there?
Yeah, fibers are more efficient always. I mean, if you think about it.
Okay, let me ask this question. Which resource is it efficient in?
Well, first of all, RAM.
Like I said, RAM was
Well,
not,
yeah,
I understand that. RAM is not a consideration.
But it is because you still have to deal with ramifications of virtual paging or, whatever, level 1 caching, like it doesn't matter.
Okay.
It is always slower to occupy more RAM.
I would say sort of, aside from his answer,
Okay, and aside from RAM, I understand
the
those.
second thing is context switching.
Yeah.
Because in fibers, it's as close to little zero context switching as possible. You change some registers, move a stack pointer. Of course, I'm sure it's more complicated in Ruby, but it's small. You're not going, for example, back into kernel space to do a switch like you would with a regular thread.
Okay. That was essentially what I was going to say. When you're context switching in the application, it's always going to be faster than if you do it in the operating system, where it has to switch the entire process as context. as opposed to just a stack pointer or two. So you get a little bit of CPU benefit also.
So if I were to repartition my queues into application-specific queues, how do I bind those queues and the queue processing to different cores? Say I'm on an 8-way core, how do I bind that?
Traditionally, or normally, you don't bind a particular process to a core. You fire up the number of processes that you have of cores, and the operating system generally will try to set an affinity for one particular processor to save caching, so that the caches don't need to be set as invalid and that sort of thing. But generally, from an application developer's perspective, you don't do anything. You just fire up the number of processors that you have of cores. That's assuming that each process can peg the core. Okay. Anything else? Okay. So that was a very long-winded way to get to my conclusion, which is threading sucks. It sucks in Ruby. It sucks overall, in my opinion, frankly. Multi-threaded code is hard to write. It's hard to debug. If you've ever had to track down a deadlock or a race condition, being non-deterministic, it's just hard to deal with if you've got bugs in there, and we all write bugs in our code. At least I do. So blocking I/O is everywhere. We know that for our message queue processor to work, we need a couple bits of information so that we can finish the processing, and getting those bits of information can sometimes mean we hit a web service or we call the database. So you're going to use it, or you're going to have blocking I/O. So what we do is use EventMachine for those blocking I/O operations, and that allows us to context switch at each of those I/O operations to some other operation that maybe can process on the CPU in the meantime. EventMachine can peg one core. We just set up multiple processes to peg all of our cores. So 4 cores, 4 EventMachines running. And that saves us a lot of memory. And like I've been saying over and over, Ruby 1.9 and Fibers makes evented code usable in my opinion. It looks a lot more like normal, traditional Ruby code. And that's it. Now you may apply. I'd say any questions, but